Next up we have Krishna from UC Davis. He's going to tell us about rates for flow matching on Riemannian manifolds.
All right, so first of all, thank you to the organizers, Philip and Jan Carlos, for organizing this amazing conference and the invitation. So today I'll be talking about total variation rates for flow matching on Riemannian manifolds. It's kind of related to the topic that was introduced yesterday in Nicholas's talk, right? All right, and the work is based on this following paper in arXiv. It's a joint work with Yunri Guan, who's a PhD student at Rice University, and Shiqian Ma, who's a professor in Rice University, who was a former collaborator, colleague at Davis. All right, so here's the outline of the talk. So I'll start with a brief introduction with some motivation, although a lot of motivation was provided in yesterday's talk already. And I'll introduce the basics of the flow matching in the Riemannian setup. And then I'll provide two rates, one for the case of compact manifolds and the other for the Hadamard manifolds. All right, so I come to flow matching and diffusion models and these sort of like generative AI tools from a more sampling perspective. So the starting point one can think of is like posterior sampling, just to distinguish it from like this generative AI kind of sampling. So in posterior sampling, typically we assume that we are given evaluations to the target density. So for example, you can have a density which is like of the form of e to the negative f, and then like you know the f or the gradient of f or something like that. And then like your goal is to kind of sample from this target density. So what you do is like you just define, for example, a stochastic differential equation whose equilibrium distribution is the target that you wish to sample from, and then like you design MCMC type of methods, right? But in flow matching and diffusion models, kind of, you can just think of it along with flow matching. And the concept here is that you don't actually have access to the true target density or any gradient or function evaluations of that. Instead, you're only given samples from the target density. And then given those samples, your task is to generate additional samples from the target density, right? So in some sense, there's two kind of things going on. So first thing is like you're not kind of sampling alone, you're kind of learning to sample based on the data that is given to you in the first place, right? And the second thing is that the way the sampler is constructed is also slightly different in some sense. So the sampling problem itself is kind of recast as a transport problem through like a designed or learned velocity field. So the velocity field is the thing that is learned based on the data, and then you just like discretize or integrate the velocity field to get a sampler in some sense, right? And this sort of framework was developed by three groups, as was told yesterday, simultaneously around the same time, Alberjo and Van den Eyden, Lippmann et al., and Liu et al., in the context of flow matching. And there's some slight variations, but they're all in the similar ballpark. The object that I want you guys to keep an eye on throughout the talk is this velocity field, right? So that's the only thing that's going to drive the sampling itself in some sense, right? So what is the velocity field in our context? So for example, suppose that you're at a particular point on the space. The velocity field is going to tell you in which direction to go to, and then like how fast you should travel, and this sort of information is provided in the velocity field, right? And as the particle moves, the entire distribution itself is transported. So there's like this transport viewpoint in some sense here, right? And typically people construct like deterministic velocity fields and stochastic velocity fields. In some sense, in a manifold, I'd like to argue that like the more deterministic you are, the better you are for both theoretical analysis and implementation purpose, in particular the implementation purpose, right? All right, so now where does the geometry enter the problem? So basically in many problems, like for example, the predicting the events on the surface of it, like earthquake and these sort of climatic events, like the problem is modeled as like generating data on the sphere, for example. And in like RNA sequence modeling and material generation, some of which was also alluded to in many talks yesterday, you work on the tori, and then like many other applications include like Stiefel manifold, SPD manifolds, and SO3 and things like that, right? In robotics, you have SO3, for example. Some of it is compact, some of it is not compact, but Hadamard and things like like that. I'd also like to highlight that, so the works before that I introduced were basically like proposing flow matching in the general Euclidean setup, but this paper by Chen and Lipman in 2024, they kind of proposed like the version of flow matching for the first time on the Riemannian manifold and things like that, right? All right, so just to summarize the problem in a single slide. So M is a manifold, and your goal is to construct like a interpolation PT between a simple base P0 and the target P1. And you will be learning a time-dependent tangent vector field. I call it as a tangent vector field because in this Riemannian context, the vector field lives in the tangent space naturally, which is also going to be important for our analysis later on. And then you have this ODE, which you eventually discretize later on to sort of generate or transport samples from P1 if you start from some density P0, right? And another thing I want to highlight before moving forward is that in the Euclidean setup, P0 is typically assumed to be a Gaussian density because like it's just taken for granted that you can sample from Gaussians easily on a Euclidean space, right? But the choice of P0 will also start mattering both theoretically and practically from in the context of Riemannian space, right? Because many of the regularity properties that you want to hold eventually depend on P0, but more importantly, even just sampling from a Gaussian, so firstly defining Gaussian distribution on a manifold is a different thing, but even if you accept some of the standard definitions, sampling from that is a different beast altogether. So now the question for the talk is that if the vector field is learned and the flow is discretized, how close is the resulting sampler to the target, right? So it's a kind of question that we ask in MCMC, but here the same question is asked with a learned velocity field or learned vector field, right? And in particular, we answer this question through total variation rates for the discretized Riemannian flow matching. And we have two sources of error, the numerical error, which is coming from integrating the manifold ODE, and then the learning error, which we kind of assume for the rest of the talk that we have a good learner, which satisfies some approximation property, but the error itself will just be isolated in the bound in some sense. All right, so let's go into the details a little bit more. So firstly, the general flow matching base setup is the following. So you pick a joint coupling between like your target, the base variable x0, which is given from which is coming from a base density p0, and then like x1 random variable, which is the target density p1, right? And then you construct this interpolation map xt. Which is like where the time t goes from 0 to 1. And then this map induces a marginal pt as the push forward of pi by the interpolation map it, right? And for example, like your p can be simple Gaussian, and then p0 can be simple Gaussian, and then like p1 can be like the mixture model that we have here. So along this interpolation path, you can define this instantaneous velocity as the time derivative of this xt, which is just the derivative of this interpolation path. And then you also define the expected velocity at the current location as literally the conditional expectation of the instantaneous velocity at a given time, right? And once you have this object, you can have this following continuity equation that relates the velocity field over time to the trajectory pt over time, right? So they both are related through this continuity equation. And it's kind of also was introduced in the talk yesterday on flow maps, right? Now, how do you learn this velocity field? So you learn this by kind of matching or taking a function class theta, typically like a neural network parameterized function class, and then you define a function v theta of xt comma t, and then you just match it to the instantaneous velocity field where you sample time uniformly, and then you just sample your initial and final samples from the coupling pi, right? And one can show that like the minimizer of this objective function satisfies this condition in a pointwise sense, right? So V star is always the true object, and then V hat is like the learned object, right? I kind of like denote the V hat here also as the minimizer in the population setup as well. So now, if you have this learned velocity field, you can replace the v star with this v hat, and then solve this ODE to get the sample. So essentially, what you do is you draw a sample from P naught, and then you solve this ODE, and then you just return x1, right? Excuse me. So now, so far, I haven't designed or defined what the interpolation is in some sense. In the Euclidean space, one of the most natural interpolations to do is this linear interpolation, where you define your xt to be like 1 minus t times your base, and then like t times x1. The natural extension to the Riemannian setup is this geodesic interpolation. So the geodesic interpolation itself looks like what I have written down here. So it has this exponential map and the logarithmic map. So let me just briefly introduce, just to get everyone on the same page, what these objects are. So basically, on a Riemannian manifold, the first thing that you need to consider is the tangent space. So at any point on the manifold, the tangent space is the set of all directions that you can move from that particular point. And the tangent space at a point x is always like a flat space, right? So the exponential map is mapping from the tangent space to the manifold, right? So you can think of it as like whenever you are going away from the manifold on the tangent space, you can use this exponential ramp to bring the point back to the manifold, right? So in particular, suppose that you're on the you're at this red arrow, which is on the tangent space at the point x on the manifold. The exponential map will bring you down to this green point. Bring the red arrow to this green point. Basically, that's the point you will reach by walking straight along the geodesic, right? And an intuition about that is that if on the Euclidean space itself, the exponential map is just the addition operation. So this is the analog of the addition operation on the manifold itself, right? And the logarithmic map is an object that lives on the tangent space. So basically, it's the inverse of the exponential map whenever it exists. So basically, it answers this question, so which direction should I start walking from a particular point, and how far to reach the point y along the shortest path, right? So it's going to be a vector on the tangent space. So now, this gives the interpolation. So basically, if you go back to the slide, so whenever you have this addition, so you have to replace it with this exponential map because you'll be away on the manifold, on the tangent space. And then whenever you're on the tangent space, you need to bring it down. So that's exactly why you end up with this geodesic interpolation. So you basically scale the arrow to x1 by this factor t, and then map it back to the manifold, right? And we also need this basic concept just in one slide. So we also need this concept of parallel transport on manifolds. So because, as I told, the velocity field lives on different tangent spaces as you move on the manifold, you need to be able to compare like velocity fields across the manifold, right, or along the manifold. And parallel transport gives you a way to think of that. So basically, what it does is like, suppose that you're at a point on a manifold, so on the tangent space at point x on a manifold. So you want to find like something on the tangent space at another point y on the manifold. For example, it gives us a way to do that while preserving the length and angle as much as possible, right? So in the sphere example, suppose that you're here, you can keep the same direction and then go to this next point y, but that's not a parallel transport. So you need to rotate at the right angle to preserve both the lengths and the angles as much as possible, right? That's what is called as parallel transport. All this is needed. Why? So because for this true for the true velocity field, so we need to understand what actually we are learning on a manifold, right? So on a manifold, the true velocity field is this conditional expectation of the instantaneous velocity, the true vector field. And by some basic calculations, you can write down exactly a formula for that. So if you give me the P naught and if you give me the manifold and metric associated with that and everything, you can do some analytical computation to get an exact, like a description of what is the velocity field so that you can show like regularities and things like that later on about it, right? And this is indeed the true object that you want to learn. And in given that, as I told, in practice, you just parameterize a neural network and then use it to use this objective function to learn the velocity field, right? So as I told, I'm not going to study this part more. I'm just going to assume that I'm given a learned velocity field that satisfies some approximation properties or estimation properties. So given that, just for the final time, this is the final flow matching on the Riemannian manifold that I study. So as was also briefly alluded to in yesterday's talk, we always do an early stopping in this context because, as you can see, the true velocity field itself has a 1 over 1 minus t in it. So you cannot take t already close to 0 because it's going to blow up, right? So you always pick a time t which is strictly less than 1, and then you generate k steps with some step size eta, and then you just implement this sequence to obtain a sample, right? And all this exponential map and everything can be for most basic matrix manifold. There are efficient implementations of these maps and things like that. All right, so now let me go to the rates. So before that, what's known in the Euclidean setup? So there's kind of some recent works and interest in this direction. So many papers, for example, Benton et al., Bansal et al., and Zhou and Liu study the rates of Euclidean flow matching in the Wasserstein distance. And Su et al. Considers the KL divergence. So this paper by Guan et al. Is our paper. There's one distinction between these papers and our paper. So although these papers study Euclidean space, they assume that the target density is kind of bounded in a ball or something in the Euclidean space. The support is like bounded, right? So whereas we do not require that in our work, actually our work focuses on mirror flow maps, so where the dual space is strictly Euclidean. So we relax those assumptions. However, when you're considering Wasserstein rates, one of the issues that you will immediately realize is that you will never be able to, so far at least, there is no method which gives like a fully polynomial dependence on the Lipschitz constants of your velocity field and things like that, which I'll introduce later. And there's papers by Li et al. And Liu et al. Which obtain like rates in the TV metric for Euclidean flow matching. Also, the Liu et al. Paper considers the stochastic interpolant version, which is like where they add the noise to this interpolation additionally, so which I didn't introduce here, right? And there's another line of work which is also starting to be more looked at, is just taking this Euclidean sampler and then looking at the structural adaptivity of that sampler to the manifolds, like the hidden manifold structure, right? So Roy et al.'s study that that setup, right? So in our work, for both the compact and the non-compact setting, we are going to make this curvature assumption. So we are going to assume that, so the R here is like the Riemannian tensor associated with this manifold. So I'm not going to introduce the details. So we have to have a strong assumption on this Riemannian tensor itself and the sectional curvature of the manifold. So these condition essentially, so we also assume that the manifold is complete and boundaryless, which basically guarantees that the geodesics and exponential maps are well defined. This bounded curvature operator is needed so that like you can have some good control of the Lipschitz constants and things like that, the velocity field. And one thing I want to point out is that if you're an expert on like Riemannian sampling itself, by sampling I mean like posterior sampling, like on manifolds, like for example Langevin Monte Carlo on manifolds or proximal sampler on manifolds, there it's assumed like the Ricci curvature is like satisfying some conditions typically, but for this case we need a more stronger assumption on the sectional curvature itself. This is a fine distinction, and the reason is that we'll be working with the ODEs on manifolds, which seems to require the stronger condition compared to like stochastic methods like MCN's methods or manifold, which seems to work with like just a Ricci, not just, but a weaker Ricci curvature type of condition, right? This is an important point I wish to emphasize. And so as I told previously, the vector field here, as you move along the manifold, it lives in different tangent spaces, right? So if you're in the Euclidean space, you can just define like a simple like Lipschitz condition or some sort of smoothness assumption on the velocity field. But in the manifold setup, we need something slightly more than that. So because the velocity field varies, the tangent vector, the tangent space in which the velocity field lives changes as we move. We need a notion of covariant derivative, which is basically like for the velocity field, what is the change in the velocity field when you move from a particular point in a particular direction while keeping all the vectors comparable, right? Similar in this parallel transport intuition. And then now you take the supremum over all such possible direction, and that defines an operator norm. So this kind of gives us like a rate of change of the velocity field on the manifold itself, which takes into account the fact that it lives on different tangent spaces, right? So our assumptions are going to be on this operator norm of this this covariant derivative, which I will just list in going forward in this talk. Right? So basically, we assume that the true velocity field satisfies this operator norm of this covariant derivative bounded condition. And then the gradient of the divergence is bounded, and then the time derivative of the divergence is bounded. And so I wish to emphasize that many of the papers that I previously showed assume these sort of conditions on the learned velocity field, whereas we do this assumption on the true velocity field, which is the object to be learned, right? As I told you, this true velocity field has a closed form solution, well, as a representation at least. And on a case-by-case basis, for various manifolds, we can verify this condition explicitly, and I present one result for sphere later on, right? And then now I'm going to assume that my velocity field, the learned velocity field is sufficiently accurate. So basically, because I'm on a compact manifold, I'm going to make an assumption that uniformly on the compact manifold, the velocity field is like epsilon accurate. And because it's an estimation error, I just denote this by epsilon estimate, right? And proving this rates is like another interesting question. So basically, the easier answer is like if you're looking at the ERM style of minimizer, like just the argmin of the optimization problem that I introduced, proving this result is relatively easier. Whereas if you're studying the optimization algorithm itself, proving like this uniform convergence for the result of the optimization procedure is a much harder problem. So it's an important question. For this talk, I'll just assume we have an epsilon accurate learned velocity field, right? So with this, the first result we can provide is the following. So suppose that we adopt this early stopping strategy that I showed before, and then we simulate the ODE on this interval 0 to t. And then I pick a constant step size eta, so this which is like between 0 and the c. So c is like another algebraic constant which is going to depend on all this LT and LT div and all these sort of stuff. I'm not going to explicitly write it down. It's just a curvature related constant. And then you have this another constant C Lipschitz, which is going to be another function of all the regularity constants. So given this choice of step size, which is like this small step size satisfying this less than C bound, you have a TV rate between the distribution of the output at the tth step of your algorithm and the true target density as PT. In TV distance is bounded by eta times the Lipschitz constant, and then like the estimation error times the C2, right? So now if you assume that you have a sufficiently accurate estimator, then you can kind of assume that this epsilon estimator is 0, the epsilon estimate is 0. Then one way people report the sampling complexity of flow matches is like just assume this is 0 and then see how much you want how many steps you should run to get right-hand side to be epsilon order, right? So you can do that, and then basically you will get something like this. So if you pick your eta to be like epsilon over this C-lib constant, the iteration complexity will be 1 over epsilon. So basically, it's a polynomial complexity bound, right? So the thing I want to emphasize is that the order of the C-lib, the form of the C-lib is not so important, but what is important is the order of the C-lib. Under fairly general conditions on the manifold, we can show that the order of the C-lib is polynomial in D and polynomial in polynomial 1 over T as well. So basically, poly D over poly 1 over T. Right? And this is actually an important point which is non-trivial to show as well for many cases, right? So the overall complexity bound here is like polynomial in dimension of the manifold and 1 over epsilon, and then like polynomial in 1 over 1 minus t. So while this bound may sound a little abstract, I can provide a more concrete bound in the case of like spheres. So suppose that you're working with the d-dimensional hypersphere, and assume that your target density satisfies just this boundedness condition. So it's not a degenerate target, so it's just like lower bounded by m1 and upper bounded by capital M1. And now you see I'm choosing the prior distribution as a uniform distribution, not as a Gaussian distribution, right? So it's already an interesting deviation from the Euclidean setup. Then all the regularity conditions that I showed previously for the general result, one can verify analytically, show that they are all satisfied for this case. And you can plug in every constant and whatever that is abstract here. You can compute them explicitly. You can pick your constant order step size to be exactly of this order. And then you can obtain an explicit polynomial iteration complexity bound of this order. And the bound is d squared. So now I only present for this talk the constant step size result with a more refined step size choice. Actually, the abstract result applies for like some general step size choices as well. And if you pick a particular schedule for the step size, the dependency on 1 minus t can be just, the two can be made 1, but I don't present that in this talk. All right, so any questions before I move on? Yeah, 3 minutes, yeah, okay. All right, so in the time I have left, I will illustrate a similar result for the Hadamard manifold. So one concrete example that you can keep in mind is the SPD manifold. And as I told, the state space is non-compact here, and it also has a non-positive sectional curvature, so that makes things a little more complicated. And in comparison to the compact case, we cannot assume things are uniform on like non-compact manifolds, so we assume regularities in expectation, right? So for example, the same covariant operator norm, I assume that it holds in expectation, not for all x as we had previously. And then the grad div and this time derivative of the divergence, everything holds in expectation. And here we need this additional assumption also on the learned vector field, that the learned vector field is also smooth in this sense, like of being the covariant operator norm-bounded and things like that. So one way to guarantee this on the learned vector field is just enforce these as like additional constraints on the optimization problem itself. But solving that and answering questions about that is like it's an open question, right? And similarly, the accuracy of the velocity field estimator, we assume it holds in expectation rather than uniformly like in the compact case. Then we have a similar result, except that the constants are slightly different in this case. The result is structurally the same. And similar to the sphere case, we can consider the SPD manifold, and we can work out every constant and show that every condition that we assume is like true, valid, and things like that. But the key choice that I make is, by the way, this has to be a P, not pi naught. So the base distribution, I assume it to be of this form here, not Gaussian, not uniform, right? So this is another crucial distinction. So assuming this condition holds, assuming this is the base distribution, we can show all the conditions whole. And we also assume the target distribution satisfies some exponential moment condition. And with this, the iteration complexity is now like very much increased in dimension dependency. So it's d to the 12, and then 1 minus t to the 3. So for the non-compact case, there is some rate degradation. All right, so no, I'm good with this. All right, so just a few comments. So the dimension dependency could potentially be improved with some additional assumptions or more refined computations. In comparison to the compact case, we need this moment conditions, which I think is necessary here. And all of this rate degradation comes essentially from the negative curvature assumption that we have on this case, in this case. All right, in the interest of time, perhaps I will skip this proof sketch a little bit, but I'll be happy to talk about this over tea or coffee. And just one outlook before I conclude the talk is, so some interesting open problems here are to see to develop lower bounds for this vanilla Riemannian flow matching samplers and see how good these upper bounds are. If they are not good, sharpen them and things like that. However, there's a more interesting question, which is also related to the flow maps and one-step generation, which was previously introduced in yesterday's talk. So in the empirical machine learning literature, there's this talk about like one-step generation and flow maps and things like that. And then, as we also saw yesterday, the number of steps in like a plot will be like 5 or 6 or 4 or something like that. But from a theoretical perspective, it makes sense to define the complexity of this flow matching samplers as being either polynomial in 1 over epsilon or logarithmic in 1 over epsilon. And this logarithmic in 1 over epsilon is more like this one-step generation and flow matching type of approach. And in fact, like there might be some connections between like the flow map approach and like more sophisticated integrators used to solve this, just the flow matching ODE itself. So those are some very interesting questions. And in particular, we had this previous work on high accuracy, meaning log of 1 over epsilon type of guarantees for Riemannian posterior samplers. So can we extend similar ideas to this flow map? This flow matching setup is an interesting question. So recently, there have been some work on like high accuracy diffusion samplers, but the randomness there plays a very crucial role here. And I want to avoid randomness as much as possible on manifolds because like Brownian motion, simulating Brownian motions on manifold is like a whole different beast. So we want to avoid it as much as possible, right? All right, so with this, I conclude my talk and I'll be happy to take your questions.
All right, thanks for a great talk. We're a bit over time, so maybe time for one question. Peter?
It's not worth the wait. But, So I'm curious about this t being less than 1. In the case of the compact manifold result you showed us with a density assumption, feels like then the distribution of p at capital T.
Yeah.
So no,
At
with
1.
these density constraints, it feels like P1 should be representable as P capital T for T less than 1.
Yeah.
With some other P1.
Yeah. So actually,
rid of the 1 minus T squared.
Yeah, you're absolutely right. So because on a compact manifold, you can basically go to the Wasserstein metric already. So the Wasserstein distance between like PT and P1 is like 1 minus T order. So for the Wasserstein rate, you can get rid of this early stopping altogether on compact manifolds, and we have that in the paper. I just didn't present it. Yeah, it's a great question. Yeah.
Any other questions? Yeah, Austin?
Don't require two-sided density bounds on the Hadamard case?
No, we instead need this exponential moment type of conditions.
Like, so why the difference between the two?
Yeah, so that's a good question. So right now, I don't have much intuition about this. So everything comes from like what conditions do we need to satisfy or show that these types of like regularity assumptions are holding true. So in the compact manifold, because we are assuming like uniform regularity assumptions, just the non-degenerate density seems to be more natural there. Whereas because we are having in expectation bounds, like moment conditions are more naturally appearing there. So that's the intuition that I have. In fact, actually, if you replace the uniform conditions with an expectation condition on compact manifold, you'll end up with like similar moment conditions as well. Yeah.
All right, maybe in the interest of time, let's take the rest of the questions to the coffee break, and let's thank the speaker one more time.
Great. Thank you.